So I was kind of mentioning that once we are sorting, sorting is perhaps the most fundamental and simple data structure algorithm where you give an array of numbers and it'll sort it in ascending or descending orders. Okay, so very simple algorithm, but it's computationally very complex. And that's why people have been trying to improve the computational complexity of the algorithm. So you see this, that there's so many different flavors of something so simple that you only want to sort number in ascending or descending order. Like it is quick sort, merge sort, time sort, heap sort, bubble sort, insertion sort, and it goes on and on. List goes on and on, and it gives you the time complexity of each. It tells you what is the worst performance, and the space complexity, the how much space it will use. And so the many applications, like even e-commerce, you want to see, and you're selling products, you want to see the maximum number of products that you have sold, and you want a sorted list of the products. So other is your stock market analysis. Maybe you just want to see where is maximum gain from the percentage perspective. uh, Exam scores of the entire board, and you want to rank them into an ascending order. Supply chain, that you want to deliver things and you have many orders and you want to sort them from the distance perspective. So machine vision, and I was explaining in machine vision, there is an algorithm which is called median filtering. Okay, the median filtering is an algorithm where uh, if you have an image which has this salt and pepper noise, this is type of an image, and what you do is you take a mask which consider 3 by 3 9 pixels. You sort these pixels in order and select the median, which is the middle value, and replace that with this value. Then you move the window again and again and again and keep moving this, and until you go this mask pass through the entire image, and you can clean this image. Like, so it works like a magic, and you get a very clean image. Okay, so, but this is a computationally intensive algorithm because every time you have to sort these numbers in an order or to find the middle value. Okay, it's not like averaging. Averaging is simple, but this is a non-linear operation that you're performing. So is the bubble sort, and what the bubble sort does is, this is the first type of algorithm where it compares to value and shift the maximum value, like 6 is greater than 3, 12 move 6 on the right. Then it compare these two values, and we are going to think in terms of hardware. So it is going to swap these values. It is 6 and 8, so it's not going to swap. 8 and 7, it is going to swap these values. Okay, so 8 goes on the right, and 8 and 2, it is going to swap again, and 8 is going on to the right hand side, and then again 8 and 4, and it is going to swap this. And so 8 comes here, and it'll just stack it there, and now it is going to rework the same algorithm on these 7 numbers. Okay, so again doing this. So, and then after it is done, then it is going to do this on the 6 number, then on 5 number, as you can see on your right hand side. It just keep on stacking uh, the maximum to the right, and at the end of this, so it is very deterministic, it is very regular, it is very repeatable algorithm, but its computational complexity is quite high because of all these operations you are doing it so many times. Okay, so this is the bubble sort operation. But then there is a bit more irregular, but maybe more efficient, is called a quick sort, where you have a pivot. The red color shows the pivot. The pivot values, once you are considering a window, you move the smaller value to the left and larger value on the right. And then you keep dividing this into smaller and smaller and smaller window, keep repeating this. And ultimately, by pivoting it a different part of that window, you basically sort all these numbers in an order. So this perhaps is not very regular because you don't know how many numbers you're going to get on your left and how many you're going to get on your right. And so it's not regular, but may have better computational complexity. The third one is a heap sort where you make a tree. So first number is the root node, then you put on the left, the other number you put on the right. Then you put on the left and you put a number on the right. And check this 8. If it is greater than the parent, the child greater than the parent, you swap. The child greater than the parent, you swap. So you just keep dropping, making a tree. If the child is greater than the parent, you swap. Again, you have to traverse the entire tree and get to the top. And once you are done with this, now you have to go from left to right. Left to right, keep filling the memory again, and you have a sorted list of numbers. Again, here you have a more complex data structure. And so if you are intend to implement it in hardware, there will be more intricacies to implement a heap sort algorithm. It again may be computationally less intensive, but uh, you have to, it has more intricacies if you want to do a silicon mapping, a hardware design. And remember, our interest is like if you have a 1 million numbers and you're sorting those numbers. So it's a large database of numbers, and where the software would take a lot of time, and you say, let me exploit the parallelism. Let me see that how many comparators I can put in parallel to make this algorithm run. This is another algorithm which is insertion sort, compare two numbers, and always insert, find out the next, and insert to its value. Now one goes here, no here, no here, yes, put it here. 8, no need to worry about it. 7, go here. So again, it's not very regular, number one. And the other one is you are cranking the memory a lot because all the time you are shifting the entire memory down, insert, memory down, insert. So a lot of cranking of the memory if you are doing an insertion sort algorithm. So insertion sort is an algorithm which is again doing the sorting. So is the shell sort, which is even more intricate, that mixes the two algorithms together. So um, now you need to decide, and that's one thing that we are going to learn in this course, and that is one thing I also want to overemphasize, that an algorithm that may look the best in software may not be a best algorithm for consideration its implementation in hardware. Okay, and mostly you're always going to have kind of multiple ways of implementing an algorithm in software. So you need to decide that which algorithm has the maximum affinity, hardware affinity, that which suits uh, the its implementation in hardware, where you can just roll out, because now there are physical blocks which are going to implement an algorithm, and you say, okay, this is how I'm going to implement this algorithm in silicon. Okay, so what are the consideration once we say affinity hai, liking hai, like algorithm has a good liking for hardware. Number one is how much parallelism you can exploit. This is first consideration, because usually the only reason you are implementing something in hardware is that there's a lot of parallelism to exploit. You say, oh, I can exploit a lot of parallelism if I implement this algorithm in this way. The number is second one is how much repeated structure that you can reuse. Like you just put it once and just reusing it in different parts of the algorithm the same, because you want that whenever you have committed something in hardware, it must be used maximum time. So its utilization should be almost 100%. You say, though I have like put 100 multipliers, and if you are hardly using them, you're wasting a lot of real estate and you're never using them. So you got to make sure that whatever you commit, you use that space optimally uh, most of the time. Uh, so another thing is we learn about what is pipelining, that can it be easily pipelined. And there may be several other factors that we are going to study in this course. So this course is about, again, algorithm to silicon mapping. taking an algorithm, finding all its flavors and variants, somehow knowing the how you check the affinity, the liking of an algorithm for hardware implementation, and then implementing that algorithm in hardware, having different considerations. This is what I was doing earlier. So let me just do this again for you to primarily explain. Let us discard this. So I hope you are there, everybody.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So yeah. So so now I'm going to map a bubble sort algorithm to explain that what is meant by this may be not a good mapping, but just for you to understand and the difference between software and hardware. Okay, because in hardware, I said you can commit as many resources as you may want to, but definitely everything has its own cost. And you say it compares these two. Okay, so there is a comparator.
I think screen sharing.
Screen sharing नहीं हुई भी.
सर कंटेंट शेयरिंग एंड हो गई है.
अच्छा अच्छा, मैं दोबारा कर देता हूँ. अब आ रही?
Yes, sir.
Can
Yes,
you
sir.
see?
इधर आ
So
रही है.
आ गया.
Sir,
Okay.
आ रहा है.
So these are the numbers, and you are saying that you are now going to put a comparator. So this is a comparator. A comparator has a very simple job. It compares these two number. The 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 smaller it puts on the left, and the the number with a larger value puts it on the right. Okay, and then it takes the next value, and again now you are committing a comparator. Okay, which is primarily a subtractor or an adder, so to say. So you put the smaller on the left and larger on the right. Then you have another. So you again put a comparator. You put left and right. Okay, you again put a comparator. Smaller on the left, larger on the right. You again put a comparator. Smaller on the left, this on the right. So you can put a comparator. Okay. So this is just first iteration of the algorithm. Okay. First iteration of the algorithm. And we are going to learn that this is a big combinational cloud and it's going to take too much time. You cannot clock it faster. What to do? Should you use this or should you use any other algorithm? But end of the day, the maximum number 9 is going to be here, which you are going to stack. Okay. And next time you can reuse. So it again depends. You say, okay, I want to reuse these in the next iteration. So you have to somehow reuse the same. And next time you say, I'm going to reuse these. I am going to reuse these. Okay, I am going to reuse these. I am going to reuse these. And but then you find out that you are not using all of them in every iteration. So the utilization of this comparator, if it is 10 numbers, only 1/10 only you have used it once. This is again 2/10, 3/10, and this one is the one that you are using uh, almost every time. So this seems like an implementation, but then you see that and it is only one iteration, and you say okay, what I do is after this iteration I repeat the same architecture, but then I put only these many comparator. Again, I reuse this and I put these many. Again, I use this. So I just keep on reducing, but I am just laying out the entire thing in my hardware. So I have the option is that I have. So first time I have these numbers. So these numbers goes in here, 4, 5, 6, 7, and 8. So I have the entire logic, which is number of comparators, and I get this value, which is the maximum value. I drop them down, rest of the values, and now I have another. So I'm just doing everything in parallel. Okay. I say I don't care how many comparator I'm going to use. And so this value is the maximum. I put them here. Rest of the values, I bring them down again. And I say, okay. And I again have these set of comparators. And I keep doing it, keep doing it. Okay. And finally, I will have a comparator which is only comparing these two numbers. And I have this and this. Okay, so the application is such that I don't mind having so many comparators, and I pipeline it in a way that every clock cycle I have a new array of numbers coming in, and after spending number of cycles I get the results. But every cycle, so I can have a 1 million numbers if I have enough hardware resources. I can do this 1 million sorting of these 1 million number in single cycle, in one cycle. There is going to be some latency, but every time 1 million number comes, 1 million number comes, and my machine is going to process them. And this is the power of silicon mapping, that depending upon how much resource you have and how you think about it, you can just map the algorithm in silicon in hardware. Okay, so this brings me. So everybody is here.
Yes, sir.
Okay, so
Yes, sir.
okay, thank you. So it means that you can kind of accelerate something which is worthy of acceleration, and things that are not worthy of acceleration, you should not even attempt to put them in silicon in hardware. Okay, so means that somehow you need to decide what remains in software and what you're going to take in hardware. So usually you have these multiple computer engines to select from. They may be just a laptop computer or a microcontroller or a processor, and you are implementing something which is not very exciting, just taking values from a few sensors and doing simple control, and not something very exciting. And you just microcontroller should be enough, which is a scalar machine, execute instruction by instruction basis. And then you have some machine learning, deep learning, RNN, CNN, uh, transformers, and and where you say how I'm going to use GPUs or maybe digital signal processors. And there may be something, then you say, oh, why should not I use this adaptive hardware? Or you design an ASIC, or you have something. And the best is if you have a provision where you have all these things. You are really, really implementing some very meaningful system. You have a startup and you are coming with an exciting idea, and that but implement some very complex algorithms which has to churn in a lot of data, and you say I have a unique architecture, and that's what my distinction, my positioning from the other is. And you will realize that even Intel, like a company like Intel, understanding the need, has come up with such devices which you can just get and explore that how you are going to utilize these devices. For example, this Intel StarTex 10 is a solution which has quad core ARM processor which can run Linux. So if there is something that just stays in software, you say, okay, this is the software part. Then it has some hardened floating point digital signal processing block, which is which can do floating point multiplication and addition. And then it has an FPGA fabric, which has 10 million logic elements, 10 million logic elements, which you can use with advanced DSP blocks, embedded memories, and uh, high-speed transceiver, because now you are doing something very exciting application, which is bringing gigabits of data, and they are transceiver, which could bring 56 gigabits worth of data inside your engine to churn, to do some processing and throw those out. And also the most interesting is a reconfigurable, partially reconfigurable logic, where part of your silicon is running. So you have mapped some algorithm here, and now you are changing this silicon, and you are keeping this as is, you are changing this silicon. So this is called partially reconfigurable logic, where without affecting the part which is already mapped and it is running, you can change the other. That's very, very powerful. So you have something like this. This is the Startex. Then there is another one from Xilinx, Zinc. We say Zinc SoC. We have used it in one of the applications, which has quad core ARM. It's clocked at 1 gigahertz. Then it has uh, FPGA fabric, about 22,000 to 4 lakh 44,000 logic gates, and this is kind of its diagram. So we were developing a software-defined radio, which is so complex that it has to have something running on an FPGA, something general-purpose processor, something ASICs, and the DSPs. And so we selected this. It's a 5G-inspired software-defined radio, and this is a very, very interesting product that we built on this solution. Okay, this is the team who developed this. Uh, Many of them, after working on this, got direct scholarships to foreign universities, because so rare skill of people to know these intricacies. Okay, all of them are now working somewhere. He went on Fulbright and is working in Apple. And so everybody got into something very interesting. Dr. Danish is the manager, and who was picked up by Saudi Arabia, a research organization, and he's working there. So these are some very, very valuable and rare skills for somebody to know that how these animals can be tamed and can be utilized. So there are many other options from other, because it's so fundamental to implement any meaningful system. Perhaps very interesting is this Xilinx Versal Adaptive Compute Acceleration Platform. That's what they call it, Versal ACAP. And what it does is, I hope I am still.
Yes, sir.
हाँ, ठीक है. So we'll perhaps we will not taken a break, so we will do another half an hour, and then perhaps we'll break. So it has like this Versal has three parts. One is a scalar engine. The other one is a reconfigurable engine, and then there is something where they have AI support, the DSPs, and other engine. And so you can have something which is serial on the scalar engine, something which is adaptive on this acceleration engine, and something which requires use of AI on the intelligent engine. And here, from the software perspective, that you are thinking, okay, I have some, this is firmware, but part of the software is just the here is this software application developer is working on this. There's a hardware software co-designer. There's the guy who is doing the design. There's somebody who is working on the AI part of the application. So that's how everything comes together into once you are mapping an application, a very intricate, uh, a very interesting application that has on AI, that requires AI and machine learning onto a system like this. and it shows that how good it performs for different tasks. For example, here it says for machine learning, it has latency insensitive tasks. It outperforms the GPUs, and the CPU is not even comparable. Here again, the CPU is not even comparable. The machine learning inference, you see that how good it performs. Then it is the encryption, online encryption of traffic, that how many gigabit per second of traffic this can process. And then there are the other where apparently CPU is not even have a chance to compete. And so this is for the 5G and radar signal processing application. Again, it outperforms the other competitors. So very, very interesting way of, sorry, say. Asha, now, another application is like in a modern car, as we know, there are a number of sensors. So this platform can do the sensor fusion where there are 4 HD cameras and a radar and an ultrasound sensor, LiDAR sensor, and you are doing the machine learning. So within 10 watt of power, it can basically fuse all these sensors, and that again, it requires a lot of complexity of the algorithm where you have so many sensors data and you want to fuse it. In almost all modern day expensive cars, you see all these sensors working together to assist you in the driving. And once you go to the CNN, which is convolutional neural network, and we know there are many models like RASNet is one, VGG is the other one, and LXNet is another one. And these are the giga operations that you have to perform. And I also told you most of the time, your accuracy depends how big a model that you are using in every class. So as you are moving towards the right, a specific model, it gets bigger and bigger and bigger. And it requires more and more and more and more of processing that you have to put in to implement. And it says that Versal can perform 2 times better than the leading GPUs. So here again, if you're just embedding it in low power, you need to use one such solution. So my takeaway for this course, and so I'm just talking about like some very high end things, but takeaway is for the researchers, for the innovators, for the students, and for the startups, is that think about a complete methodology, that how you should take this course and your profession. So for example, we solve problems. We Every engineering or a computer science graduate is trained to solve problem, uh, have a proposed solution, and use his scientific knowledge which you gain, do the literature review, study design, run it, have results. If you're happy with the results, do result and analysis. Usually if you are a student, you're more focused to do a publication, and and you don't really worry too much about the industry. And so that's why many of us are just focusing as a student just to increase the performance a little and just publish, and we say we have increased. And this is about the MS and primarily the PhD students. And we don't even focus on disruption. So our mind does not work that we can disrupt some way of doing how the people do things today. So we're disrupting anything, and we are hardly innovating, just a new way of doing the thing. As But objective should be that at least some of us must do the disruption, and at least the innovation, like 40% do the innovation. And innovation is like a newer way of doing the same thing and finding value in that. So from my perspective and from this course perspective, and I'll be giving you many examples, and which can be even the startup ideas that you say, okay, here's something very relevant. This relevance is important from the industrial perspective. So the problem must have some relevance. It must have some context, and you say, I have a meaningful problem. So I'm not solving just a problem. I'm solving a meaningful problem. and I have an innovative solution. And once I have a meaningful problem and an innovative solution, I create a value. And once I create a value, it can be a product. It can really, really help somebody and remove pain from working of some workflows, a problem. So that's what I want for us to think about it. For students, definitely is learning a new area, topics for your final year projects, for your MS and PhD thesis, for publications, and as I mentioned, startups is that you can have a startup. But let me now give you another example of the work of my students. Uh, so I have always like tried to um, make students solve like complex, meaningful problems. So here is one of my students who was working on swarm intelligence. What swarm intelligence does is it throws many swarms. These are kind of small agents, a piece of software you can say, which is seeing some problem at different parts of the problem, and then it converges slowly but surely. All swarms like converges onto something which is optimal, like this. So there are many swarms, and usually the design space is very complex. So whatever you are trying to do, I'll give you an example in a while. And you want all these swarms to slowly but surely converge to the optimal point, and this is called the swarm intelligence. Okay, so how it does it, like a solution, and every particle which is piece of your software, independent software, will have its personal best, that this is the best it can achieve on the surface, and with some velocity it will move to a global best. So there's a way that everyone communicates to the other, and then you find out which is the best. For example, if you are trying to find out uh, the minimum of y is equal to 3x square, though this is a stupid problem to solve from swarm intelligence, but 3x square plus 2x. Okay, 3x square is fine because it's just a parabola. And you can have multiple swarms. You throw those swarms on it, and slowly but surely, every swarm will move down and finding out where the global best is. And slowly, they all will converge to this point and tell you that this is the minimum. Okay, so that's the algorithm. And he was using it to localize the number plate uh, of cars, taking in a video. So there's a video, the cars are coming. In order to use an OCR, first you need to localize the number plate. And as you know, in Pakistan, we use different types of number plates. Everyone kind of has an option to use a number plate which is different from the other. So somehow all these swarms, you throw them on an image, you don't know where the number plate is. For example, it is here in this image, it is here in this image, it is here in this image, it is here in this. So in every image is going to be at a different location. So what he would do is he would throw a lot of swarms, and all these swarms slowly, knowing some of the characteristic of the number plate, I'll just go and converge on the number plate. But it was taking forever for even on a single frame to find out, because of the number of swarms and the algorithm and the way they all are moving. So it'll just take forever, and we wanted to have like many, because usually if you put this in a real life, so you got to do this for many cars. Every frame may have multiple cars, and you got to figure this out for multiple cars. So we decided to implement it in hardware. Okay, the algorithm, we decided that all swarms, and we wanted to make a repeatable architecture where they have to communicate with each and every one. Why? Because you have to find out the global best. Everybody has to have the global best, and then every swarm has to move in that direction. So we have the logic. We call them processing element, processing element, processing element. Every processing element is implementing a swarm, and then a router. It's a system on chip solution. It's a PhD work, so don't worry if you really don't understand it. But I'm just telling you that how you can have something complex algorithms that can be laid out in silicon and becomes very powerful and meaningful in a very small cost, a very small area. Uh, you can do uh, processing of many uh, uh, images at a very high speed. On if you do an algorithm in silicon, definitely you have low cost. You have that's something which is very specific to doing this. And so this is the algorithm in every processing element, and then a way that they communicate with each other through a network on chip. And so he also published this. You can find out his paper and embedded architecture, and I'll share it on the group as well. The real-time object detection in digital image based on niching particle swarm optimization. So this is his name, Shahid Mahmood, and here is the title of his thesis. Then this is Dr. Farhan, who will also be part of the group who will be teaching you. And this was his PhD. And we claim this is the smartest, the thinnest, the smallest AES engine that does a very high speed AES encryption as an 8-bit systolic architecture. Okay, I'll not get in because again it's the PhD work. So we did a lot of innovation in implementing it as a systolic architecture. But AES is something where you have plain text and you have a key round. So first of all you need to expand all the keys, then you take a key and then do add round key, then you do byte substitution, then you do shift rows, and these are the different parts of the algorithm. The mixed column is more intricate. The most intricate is the mixed column algorithm, where you are multiplying a matrix and with some numbers, and then again you do add round key, and you keep doing this for n-1 times, and finally uh, you run the final iteration and you have the ciphertext. And precisely the same thing you do in the reverse order. Once you have a ciphertext, almost the same thing you do in the reverse order. And then almost once you are extending the keys, you kind of doing the same thing. So at top level, we have like the data coming in here, and data is 256, 128. uh, you 88 1 byte of data, you put 4 by 4 array, 16 into 8 bits, and then you run it through uh, this process, and then at the end of the day you get 128-bit of ciphertext out. uh, and again, I'll not get into this, but as I explained, the complexity and the innovation was in the mixed column and making it a systolic architecture, which just automatically keep using this, and end of the day multiply uh, a vector with a matrix. So this was his work, systolic implementation of an architecture. So now let me come to the architecture design and why I think that it's somehow like more of an art and less of a science like. But still, you got to learn that how you are going to design an architecture. So I'll just get into the architecture now. And this is again an interesting part, that once we say architecture, okay, so for example, on the left you see uh, a railway station in Lahore, okay, platform number 2. So and what you see on the right is Melbourne, Australia. Okay, so both are doing almost the same thing. Perhaps this railway station was constructed or built and designed as a pre-partition, like in the Britishers, they primarily designed it, and we are using it still today. And then you find out many more.
सर कंटेंट शेयरिंग खत्म होगी है, काइंडली दोबारा इनेबल कर दीजिएगा।
So I'm back. Okay, thank you, Imran. I'm so uh, let's go back to the example. Uh, I can have this window. Okay, so I was talking to you about the architecture. So you see here a railway station um, in Lahore and a railway station in Melbourne, primarily doing the same thing. That just the train will stop and the people will get on the train, and so there are platforms and there are different platforms, and somehow you will figure out that on which platform your train will come when, and there is this yellow line that you must not cross and don't hit yourself and don't get under the train. So, and then is here is another uh, station. I don't know where it is. It's so beautiful, so elegant, very complex structure. Uh, Primarily doing the same as I am also outside Pakistan. Actually, I'm in London, and it was just yesterday. I was on a railway station. This is me yesterday on a railway station, and as again, a railway station looks like though more elegant than what we have in Lahore or in any other city of Pakistan. But end of the day, it was just a railway station giving some information about the train, on which platform the train is coming, and then you have to go uh, and across somehow the track to go on the other side and get onto the platform on which your train is coming. And you go and sit in the train, and then just same. So architecture uh, always going to be different for the same thing, always going to be different, because the way, and that's the beauty of the architecture, there's always going to be different. That's why you see an ARM and a MIPS and a Intel processor and the GPU and this and that. So whenever you think about the architecture, it is going to be different. Okay, so interestingly, my first publication was on extracting parallelism from an architecture. It's a pre-NVIDIA. So I'll I'll share with you this paper as well. There was a conference in MIT in 1995, and the topic of the conference was all neural networks dead, because people thought that neural networks are computationally so intensive that a sequential machine cannot handle that complexity. And I proved, and because my PhD was sponsored by Analog Devices, and I was working with MIT Lincoln Lab on an 8 by 8 processor array. And they wanted me, though the MIT Lincoln Lab was implementing that on implementing a radar application, but I was tasked to implement some commercial applications so that they can sell that computing platform, which has 64 digital signal processor on it commercially. So this was the first application I selected for mapping, and I could able to extract parallelism, that depending upon how many processors you have, and you can do the training, which is kind of the basic of even these large language models, that they are, once they are to be trained, they got to be trained through a back propagation, that you got to compute an error and then back propagate it, which basically then adjusts all the weights, and then you have billions of these weights and you run it so many times. And so that's what I tried proving, that uh, there is a parallelism to be exploited, and that's what I exploited. The second thing what you need to learn is, once you are designing an architecture, may it be a house, or a commercial market. So there are different components that in case of a processor, you have memory, you have interfaces, you have actually machines that are doing the computation, multi-core machines, then there are caches, and somehow you got to place them. So somehow you got to place them uh, at different locations. So it's a physical area like a plot, and you got to place them. You got to make sure things that are to communicate from the outside world, you got to place them on the periphery. So you say place them on the periphery, so that you don't have to really bring all of that, all don't want to make all the data travel all the way inside where they can be placed on the peripheries. So a placement problem in a chip design and how you are going to partition the functionality becomes important. This is again my publications where my PhD was also funded by a packaging center at Georgia Tech, and they wanted me to do if there are multiple nodes and they are communicating with each other, and they wanted to put them on multi-chip modules on multiple chip and all these chips on one platform. And so I came up with a mathematical model which could actually uh, could partition them in a way that there's minimum uh, communication. So most of the communication remains within each module, and so that whenever you get down onto a chip, you dissipate more power. There are more delays. So you want things that are communicating more. They got to be placed together, and you try that once you are going off chip, you must have like minimum of the communication. So then comes the house. Once I was started engaging with an architecture to design my house, it was always the chip designing experience, the logic partitioning experience, the workflow experience, the data coming from the periphery and then going into the chip, getting processed, how to do the clustering, how to put which cluster where, and that was running in my mind, and I was kind of communicating. There's an interesting part I wanted to just show you. So the architect asked me to fill up this form, which kind of uh, uh, list all my requirements. So he said, okay, what do you want? A multiplier and an adder? How many multiplier? How many adders? How many memory? Kind of that. So this is like he has. These are the things that and how many of each. And so the first part, and then he sent me, okay, this is where he is going to place different things of my requirement based on like his experience. And then I started uh, going through, what I've learned, that the flow, what has to be on periphery, what has to be like together. So very, very interesting design experience that I would just keep communicating with my architect. No, this is how I want different placements, moving things around based on the simply the workflows, the how the primarily the experience in the chip designing, the architecture that we do, and many communication with the architect and sending them again and again, making these drawings and sending them back to the architect. And because to me it was like these were the components, like they're good to be uh, bedrooms and lawns and atriums and drawing rooms and the neat kitchen, and the kitchen, like everybody has this, the worker quarters. And so I just wanted to make sure that uh, the periphery should have the workers coming to the kitchen and going to the places, guests, outsiders, this, the family, like this, and could able to uh, come up with an interesting layout, uh, and then uh, again communicating the layout with the architect, and then he came up with the design, which I believe is very functional, and then his own things. But then comes the definitely the material, that how we are going to construct the house. So if I come back to now the silicon, uh, like bricks, chip is made of transistors. So, uh, but almost as I mentioned, as like physical layout of things, and going back to the abstraction level, that you have a problem, but you want electrons to do the work. Okay, they are the workers who are going to accomplish um, uh, the task which you have given to them. So in between there are many steps. Okay, so a chip is made of transistor, like a house maybe is made of bricks, so a chip is made of transistors. And the first transistor came into existence, like somebody who designed it, he got a Nobel Prize for that. So it's such a big invention in the history of mankind, the first transistor. Okay, and then the Intel came up with this 4004 processor, 404 processor in 71, which has 3000 transistors on it. Okay, in 2019, Intel has a processor which has almost the same transistor as the number of people. Right, it's a 10 billion transistor. It's the first chip. Uh, and you can see, because the transistor, they got to connect with each other, and here are the things that the data has to come from outside. So I think it is also a piece of art, because it's all crafted from hand, and it's perhaps placed somewhere, maybe in New York Museum of Art as well, perhaps. But now it's the physical thing. So once you are saying silicon, silicon is a physical thing. It's a transistor, uh, and mostly there are two type of transistor: an NMOS transistor and a PMOS transistor. Okay, so there's a silicon, then there's doping, then there is the metal oxide, and so it's a physical material. And there used to be like thousands, and there used to be millions of these, and there used to be billions of these. But end of the day, these are the transistors. And because we, from the architectural perspective, if you go into the VLSI design part, where you want to design something at this level, it is fine. Otherwise, you should never worry about this level. But why I am just covering it, so that you know that there are physical things. What makes an electron to dance in your in the electronics are these transistors. So through this gate, they control whether an electron which is coming from the source, the power source, should go forward or not. If it does not, it is a zero. If it does, it is a one. So this power which you are sourcing your chip with, every transistor in the chip is to be powered. Okay, and this is the power which is pushing the electrons. And these electrons, through the logic that solving the problem, either would make this gate, which is an NMOS gate, and a PMOS gate. They two together will just decide whether this electron should go or should not go, should go or should not go. If it goes, you say it is 1. If it does not go, you say it is 0. So the logic is either a 1 or a 0. So this is together. For example, this is an N-type NMOS. If the gate has a 1, okay, so this acts like a closed circuit. It is a ground. Once you have something short circuited, you have a 0 here. So 1 will be converted into a 0. On the other hand, if it is a p type, you have a 1 here. uh, the characteristic of the material and the doping and everything is such that uh, it will act as an open circuit. So here, because it's not short circuited, so it will be a 1. So a 1 here will be a 0 at the output, a 1 here will be 1 at the output. So they are complementary to each other. That's why they are called complementary MOS or CMOS. Okay, so a 0 here is an open circuit. It's now reversed, that if you are 0, it will behave like an open circuit. So the ground will not ride in here. Short circuit nahi hai, 0 nahi hoga. And so it will give you, if it has a voltage here, I'll just show you 1. On the other hand, if it is a 0 here, it'll act as a short circuit, and the ground will be short circuited, and it'll give you a 0 here. So interestingly, putting two of them, and always this is how your entire chip is made of these two transistors, an N-type and a P-type. Okay, so they are either in series or in parallel, but these are physical devices like bricks in a house, which are constructing uh, the entire logic, and all they are doing is just making sure whether electron from here should go here or not. Okay, so this is where, so you have to power. So there is a power line and there is a ground line on a chip, and many of these lines, and all your gate the logic is within these, okay? So the power line and the ground line, the logic fits in there because every transistor has to be powered, and with their combination, you make the logic. For example, this is the logic of a NOT gate. NOT gate is if you put a 0 here, okay, so it will come out 1 because this will be short circuited. We know the P type, and N type will be open circuit. So this VDD will come here and ground will not affect it. So you will read 1. On the other hand, if it is 1 here, this will be short circuited, this will be open circuited, and the ground will come on the output as a 0 volt. So I use read a 0. So that's how the NOT gate would work. That a 0 will short circuit this and open circuit this, and we're never ever going to come back to this, uh, but I want you to understand that end of the day, who makes the electron to dance and do what you intend to do? These are the transistors. What transistors are doing based on whether at their input it is 0 or a 1, and they let the electrons go through it, or they stop the electrons not to go through it because they'll behave like an open circuit. So this is the inverter. Then you can have an AND gate by having this is a NAND gate. Okay, so NAND gate is this much. So you are putting the two P type in parallel and two N type in series, and we can go through the same logic. What happens if you have 0 here and 0 here, and we know that which will have an open circuit and closed circuit, open circuit and closed circuit, and very easily you can go through the logic that yeah, it makes sense. This is a NAND gate, and if you want to now make an AND, so you invert it, so it becomes an AND gate, and similarly a NOR gate. So so that's just we'll spend like a few more minutes. That has uh, brings the Moore's law, that Morse said in 1965 that the number of transistor on a chip are going to be doubled every 18 to 24 months. Okay, and he made like this prediction way back in 1965. He is Gordon Moore, the CEO of Intel, and this is his paper, which he wrote in 65 based on what was happening in the history previously. He said, oh, they are going to be doubled every 18 months. And amazingly, uh, Intel is like till many years. He was again Mr. Gordon Moore in 2003 saying no exponential is forever. How can an exponential be forever? It'll go to infinity. And he said, yes, no exponential is forever, but we can delay forever. You can just keep on delaying forever. So because exponential hits the infinity. And Intel is just doing this in 2011. They have a 22 nanometer. This is how small and refined the transistor you can actually make. Whereas this Intel first microprocessor has 10,000 nanometer. It became 22 nanometer. They placed 2.9 billion transistor into an area of the size of a fingernail. And this is now Intel claiming that by 2030, there's going to be a chip which will have 1 trillion transistors on it. So you can just imagine that where the technology is moving and becoming finer and finer from 10,000 nanometer to 3 nanometer. Uh, and uh, uh, and as they are moving, they are pushing, they are coming up with the better and better ways of designing a transistor. And a trillion transistor, no human being can program an animal which has 1 trillion components. So this is where I will stop, but I just want you to know, this is my last slide, that there is a problem that you want to solve, and you write an algorithm, and you define an architecture, and you design a front end, and you got to do the verification of the algorithm and the architecture and the front end. And then those of you who wants actually going through with there are transistors being used, and you have a gate list, and to the backend place and route. But interestingly, everything is becoming easier. Why? Because 1 trillion or so many billion transistors, you cannot go individually and design and program. So there, we call this a level of abstraction. That is what makes this course interesting. That level of abstraction. The level of abstraction is increasing, and that is making the whole thing easier. So here is above as you go is the level of abstraction, and here you go is the skill as an electrical engineer, and on this side if you are just a computer scientist. So everything is becoming moving towards the left, means even a computer science graduate can learn and design these things, because you are never ever going to go and see this NMOS and CMOS and the transistors and how the transistors work. You are never ever going to be worried about that. All you have to be worry about is in hardware things happen in parallel. Everywhere things are happening. So that is the only thing that you need to just remember. So this level of abstraction makes you uh, do the architecture, do the silicon mapping, and as it is moving the algorithm, even in many cases you're not even a computer scientist, through uh, this generative AI you can implement algorithms. And that's the interesting part, that now so focus on the architecture, focus on the verification. That's my perspective. And this is where you are a hardcore electrical engineer, and this is where uh, you are nobody. This is where you are a computer scientist. So it's like it's covering the whole spectrum. So people can have a problem, design algorithm. Computer scientists can design architectures, front end to the verification, and then they're hardcore people because they need to understand a lot of intricacies of things, not at the transistor level, but what the transistor behaves. So that's why my plan for the first is, next class we will discuss what is abstraction and how we can design these complex things having at very high level of abstraction. So I think I just stop here. And if you have any questions, because from my perspective, I have not taken any break. So this is pretty much what I want to cover. And you can ask questions now or on the group. You can just shoot anything that you want to ask. But I hope that you understand what this course is going to be about, and who should like continue taking this course. And you can even ask others. Jeet, question?
Yes, sir.
Ask.
Sir, about the layers, like I'm a bit confused, like how we are gonna divide it into like OSI model layers. Like once we are dealing with algorithm and then we implement this algorithm into the hardware, and then we have to select the hardware. We use the FPGA, Intel processor, whatever we prefer. So how we are going to do the physical or data link layers division here?
Actually, those are like logical partitioning of something, has nothing to do with hardware. OSI layer has nothing to do with these layers what we are talking about. वो जो है वो भी abstraction में जाती हैं. मतलब उसका ये होता है कि once you are the lowest layer, which is the physical layer, where then you have a physical layer where you need to have bits converted into a signal that you transmit. At a high level, you have a MAC, which is medium access, where you got to access the medium so that you can use the wireless channel or a fiber to send something. So this has nothing to do with those layers. It is only you have a hardware, and part of the algorithm is running on not on your programmable processor, but running on the hardware like GPUs. If you have some experience with GPUs, so it's almost like that you are running something on the GPUs.
Okay,
Sir,
sir.
I
Okay,
have a
got it.
question.
GG, please.
Sir, I don't know much about hardware, like how transistors, multiplexers work, but I know much about ML algorithms. So, what do you suggest? Should I continue this course?
Yeah, continue this course, because you are not going to see these transistors again. Okay, so So we are not going to design things at the transistor level. We will be designing things at a higher level of abstraction. So if you know the machine learning and the programming, you should take this course. No issues.
Hello, sir.
Ji.
Sir, what would be like the best way to go about? Is there any sort of requirement for like, is there any going to be a let's say semester project for this course? Are we free to choose from the algorithm that we want to implement in the hardware? How would that look
Yes,
like?
yes, because I'll be covering that how we are going to have different parts of the. In fact, we actually wasted like I thought that I'm connected, but here is the. Can you see the screen?
Yes, sir.
So there are going to be labs and assignments. Assignments are to be developed alone. There's going to be a final project and the midterm and the final. So, and that's how we are going to go about it. Uh, so there will be a lot of hands-on. This is primarily a hands-on course. It's a lot of hands-on work that we need to do in this course.
Sir, I have a question.
Ji.
That we have to translate the ML part or we have to design hardware?
Yeah, you need to have the ML part. You need to take the ML part and design the hardware to execute that ML part, machine learning part.
Sir,
ठीक है, जैसे मैंने sorting का algorithm किया था ना, the sorting, that you have the sorting and you just do that sorting into having multiple comparators placed so that they in parallel do all the comparison in parallel, not sequentially as is done in the software.
सर
Yes, yes.
एक चीज मैंने पूछनी थी कि आजकल
जी पूछें. So the next class will be on campus. So I would suggest that most of you who can come to the class, and inshallah we will discuss it there as well. और अगर आपको लगता है कि ये बिल्कुल ही beyond your comprehension है, तो I would suggest you not to take this course. But if you think that you can just handle, you can know how to program things and you have understanding of the algorithms, only then you should take this course.
Sorry, sir, I have removed. So I have an issue in connection. So I have a question like we have mapped the algorithm or translate the algorithm or we have designed the
Map
hardware.
the algorithm. You have to map the algorithm.
We are not design hardware for specific algorithms.
You will design hardware for a specific algorithm. Yes.
Sir, Assalamualaikum. Sir, I have a question regarding the abstraction levels that you mentioned. Sir, इसको अगर हमने translation करनी है from algorithm to hardware, तो sir इसमें how do you translate it in the form of code generators? अगर उसका कहीं से code generator से क्या difference है? और sir दूसरा, how do you
let me answer your question. You समझ आइए. ये कि we will generate code, but first we will design an architecture, and looking at the architecture we will generate code.
Sir, sorry, why I left the meeting. Sir, second part इसका था कि sir, how do you compare it with high-level synthesis tools, which are also doing kind of the same thing but in a different way?
Ji, precisely. So high-level synthesis tool can also be an option, but they give you very little control on your design. लेकिन हाई लेवल टूल में भी आप एल्गोरिथम एक आर्किटेक्चर से डिजाइन करके उस तरह से लिखकर उसको दे सकते हैं. तो यस, हाई लेवल synthesis tools are option to be used for the architecture design.
सर मैंने ये पूछना था कि आजकल एनवीडिया का जीपीयूज का हम काफ़ी सुन रहे हैं कि मशीन लर्निंग और एआई के लिए, लेकिन आपने जो ग्राफ दिखाया था जाइलिंक्स वर्साल का कि उसकी
वो आउट परफॉर्म कर लेता है इन्हें, क्योंकि जीपीयूज के साथ अपने मसाइल हैं। उस पे पैरेलल थ्रेड्स आपके चल रहे होते हैं, प्रोग्रामिंग करनी होती है, उसमें डेटा मूव करना होता है। तो ये जो है ये प्लेटफॉर्म काफ़ी ज़्यादा, और बहुत सारे और लोग हैं जिन्होंने आर्किटेक्चर्स बनाए हैं जो आउट परफॉर्म करते हैं जीपीयूज को। तो ठीक है, चलें इंशाल्लाह नेक्स्ट टाइम जो है प्लीज बी देयर इन द कैंपस सो दैट वी कैन हैव मोर
I have a
इंटरेक्शन।
question.
जी जी।
Yes, sir, I'm working in a lab in USA. So our lab is going to tape out chip, actually an SRAM, truncation SRAM actually. So we are going to tape out.
We lost you again.
Sir, someone removing me again and again. I
ओह
think
मेरा
it's an
ख्याल है
issue.
आप ना ऐसे कर लें
Hello,
जैसे।
hello. Sorry, hello,
जी जी
sir.
जी जी।
I'm sorry. I was just removed. Yeah. So what I was saying that I have been assigned, like my task is basically when the chip will be taped out. So I have already designed an AI accelerator. It's a simple AI accelerator, and it's being taped out now from eFabless. So what I'm been assigned now to integrate the taped out SRAM, which is going to be taped out within a couple of months, with an FPGA board so that I can, whenever I have to give the weights and biases, I will give those weights and biases using the SRAM we are going to tape out. So I was so I just want to have a hint what should I know about interfacing the SRAMs with FPGA board? Yeah. So I have
Yeah,
to do the interfacing of SRAM with FPGA board basically.
G FPGA board, or you want to design an FPGA board where you put your SRAM and the FPGA so that FPGA can basically interface with the SRAM जो भी उसके आपने IOs SRAM के बनाए हुए हैं, like where you have to give a clock and then there is an address and then there is a data and the whatever the protocols you have. So you primarily control it through an FPGA to check whether your SRAM works properly or not. You know, so that is how, but you may have to do just your SRAM chip coming out, be part of the FPGA board, and where you start writing the logic on the FPGA to ensure कि उस SRAM को आप उसको read और write कर सकते हैं उस पे ना। ठीक है, if you have like other questions, like feel free to just share it with me on the WhatsApp, or I'll try to answer them. Or then next class, inshallah, we will have it on campus. And I'll also find out, because there are people who have a lot of experience, there are people who are very new. So we need to see that how primarily we run this course, inshallah. तो हम next class में इसको discuss करेंगे. Thank you. Thank you very much for being here.
Thank you, sir. Allah
If
Hafiz.
someone
Thank you, sir. Allah Hafiz.
Love it, sir.